Okay, I guess maybe we can start and people will join us as time goes by. Well, thank you for coming. My name is Milos. I'm a CTO and co-founder of ThinkSolver. Welcome to this presentation. Just a brief history, in case you don't know, ThinkSolver is a company co-founded in Belgrade by my college friend Arko and me 2015. And basically we are a team of data scientists, data engineers, and developers that work on building and deploying data products, whatever that means. So our main talk for today is the coding portion of data science. So should data scientists program and how much of the programming is required? So I can just answer yes and then leave just a space for the questions so we can finish this. But I had another idea for today. So when I started preparing for this presentation, my dear colleague Valentina told me, well, that's a good talk, but there is one problem, you're not a data scientist. And that's true. My background is actually data engineering, so I'm not a data scientist. This is just a perspective from my point of view. But there are a few reasons why I care about the topic. So I named it here. For example, as a technical lead, okay, is this working? No, never mind. As a technical lead in a company that works on building data products, machine learning-based solutions, I really care about the skill set that we have in the company so that we can really build products that matter. As someone who is building data products, I need to make sure that they are really easy to use, that our clients can really implement them in their environment, they really use them for their daily operations. And on the third side is data engineer. I work on daily basis with data scientists, so I really like if they know how to do some part of this work so I don't have to do it as a data engineer. So let's start with this slide. Is it possible to become a data engineer, to become a data scientist, to work as data scientist without coding? And what the industry tells us, well, in most cases we are using the algorithms that are out there for decades. So they are already coded into some platforms. We can use them out of the box. And there are some platforms like Google Cloud, AutoML, DataRobot that really allow us to run all these models with drag and drop interfaces. So we really don't have to code them in Python, in R, or some other languages. So everything is pretty straightforward if you look through it from this perspective. But on the other side, if you look at the market, what does the market tell us? So this is a Glassdoor research from, I believe, 2016. So what do companies that hire data scientists, what they require as a skill? Well, actually, they all require a lot of programming. So all of these technologies here actually are related to programming. So I guess the companies still go to data science projects from this side. So we really do need programming. And we know this famous Venn diagram, what data science is. So by data scientist, we refer to a person that has some machine learning, math, statistics knowledge. So basically, we can implement some algorithm to solve some problem. On the other side, it has the domain knowledge, like a business expertise, so you can identify some problem that is relevant for the company, so that this person should also know how to try to answer this problem. And on the third side, we have computer science as a way to actually implement all these algorithms to a specific domain knowledge and use them as a software. In general, we are trying to build some software as the output. So this is the talk for today. So how much of the computer science and what actually of the computer science is required for data scientists today? So how we typically actually become data scientists? Well, nowadays we actually have the academia that provides really good courses to become a data scientist through bachelor studies, through master studies, where we can basically go to pursue a university degree in data science. But the orientation of most of these programs is oriented towards machine learning. And I can say that, machine learning is just a portion of all the things that we refer to as data science. So the academia is mostly oriented on modeling, like representing some problem through machine learning model evaluation, how to work with different data, how to build features. But there is a bunch of stuff that basically there's no enough time for academia studies to refer to. For example, problem formulation. In most cases, we learn regression. So there is some data set, we already know what is the target variable, we already have the data set prepared, we already know what is the problem that we are working on. So we, as someone who is learning how to become a data scientist, we don't learn so much how to formulate a problem, what is the relevant problem. Of course, there's always ETL. Modeling is just a small portion of the work that we do as data scientists. In most cases, we just try to transfer data from one place to another, from this format to the second one, because data is never structured in the format that we can really use to build a machine learning algorithm. We already need to do some tweaking, some data transformation, and of course, to build some features, which is really the essence and maybe the art of machine learning. And hopefully at the end of this process, like we have ETL, we have model, we have evaluated our model, we know that it works, but then comes maybe the most painful part, like how to put everything into production, how to run this code into production, how to debug if something is not working. And at the end, of course, the context. So from which context we are looking to this solution. Let's say we are working on a recommendation engine. Context here is really important because it matters whether this company wants to upsell to the existing clients, to gain new clients, so whether they actually have a strategy of growing their business or selling more. So it really refers to, at the end, it needs to go back to the context in which we want to implement this algorithm, because the strategy won't be the same for the company that is the leader on the market or the company that is the challenger or the follower, or basically for the company that is just entering some market. But of course, we cannot blame the academia for that. First of all, there is so much hype in the data industry at all. We on a daily basis see that there are some new architectures, some new algorithms, improved algorithms. So it's really hard for academia to keep a track of. Most of the programs at the universities last for 5 or 4 years, and 5 years ago we didn't have I don't know, GPUs, Kubernetes was just entering the market, we were just starting to talk about Docker. So all of these topics in most cases are not covered with the academic programs because it's really impossible to do. There is basically not enough time for to address all of these topics and to structure them properly. So yeah, I believe the academia is focusing on one of the really most important stuff of the data science. It's actually how to work with the data, how to extract the insight from some data set, how to make sure that this insight is relevant, that it's true, that we can really make some decision based on it. And then there is also KAGGLE. It's really, I believe all of you know here what is KAGGLE, so it's a really popular platform for learning data science. How it typically works, you basically go make an account, open an account at KAGGLE, you join some competition, companies there post different competitions, so you find a competition that you want to work on, then you build some models, submit it, watch the leaderboard, and hopefully win some prizes on KAGGLE. And it's really, KAGGLE is really one of the greatest resources of how we can learn data science. Although I'm a data engineer, I'm spending a lot of time on KAGGLE just to go through the code that people are writing there to see actually how to build some features. And the way some people are working with the data, it's really a poetry, it's art, it's not just engineering. Really, the people can get really creative, and I believe that is the essence of the data science. But there is also issue with the KAGGLE. All the problems that we are working on are already formulated. So the company submits the data set and they say, okay, build me a recommendation engine for this. I don't know, do a customer segmentation, build a neural network to identify, I don't know, which the letters to transfer them to text or something like that. Data sets are already prepared and labeled. So we already know, we have most of the features prepared, data sets are in most cases cleaned, and we know what are our target variables. So we don't need to build them from our raw data sets. And of course, lack of decision process. So this model that we will build on KAGGLE, how it will be used. So it really makes a difference whether we are building, I don't know, a recommendation engine that will work in the offline mode, and will be running, I know, once a day, once a week, or we are building a recommendation engine that needs to support e-commerce solution and run 24 hours with really tight SLAs. Yeah, but also we cannot blame the KAGGLE for this because there's just too much stuff that needs to be covered. So this is one of the areas where KAGGLE is specialized. And why is all of this relevant? So the way that in many cases people approach data science does not take into account what does one decision-making process look like. So by learning data science, we tend to work in offline mode in our Jupyter notebooks. And here are some requirements and the characteristics of the decision-making process. First of all the processes that we operate today need to be adaptive because our strategic and operational business models change day to day. We change the way how we create value for some customers, how we deliver value to this customer. So also all of the things that we build also need to be adaptive. Of course, contextual, because everything that we work on, not just in data science, but in general, requires the context. So why do we want to achieve this, in which circumstances, what is the internal atmosphere, what does the market look like? So we need to really take care about it. Of course, regulated, especially data scientists tend to really adore some algorithms that they really like to build neural networks to implement deep learning. But if we are a bank, we will probably struggle with implementing deep learning for the customer risk analysis, because some areas of our businesses are really highly regulated, and there are strong limits what we can do and what we cannot do. Of course, the decision making needs to be done in real time. As you all know, the value of each information drops over time. So whenever there is when information is generated, there is the highest value of this information. If you use it immediately, tomorrow this information maybe won't be relevant. And of course, interrelated, because I've never seen a process within the organization that doesn't depend on other processes that the company is running. And what that means is that it depends not only on one application, but there are many, many applications that we use within our companies. So we need really to think, when we are working with the analytics, how this is going to be served to all these applications that there are out there for a company. So which CRMs do we need to integrate to, which campaign builders, marketing tools, so different stuff that we really need to consider in order to build a solution that needs to run in production and really help some business to actually get the insight for decision-making process. And one of the things that not only data scientists, but also data engineers, what we believed while we were pursuing our academic degree, or when we started working with the data, we had basically the idea that the department that needs to provide us the data, that they will have a dedicated person that will stand with us 24/7 as long as it takes before we get to connect it to the right data set. In the organization, it's never like that. In best case, you get immediately VPN access or, credentials for the database, and people just let you go and dig through the data and actually go search for the data that you need to have. It's really hard to actually find, if you are searching for a certain data, it's really hard to actually find the people that really know what all of these columns mean. So really, you need to work a lot to demystify what's there in the information. So we can really benefit here, at least from the different network protocols and connectors, and how to implement proper security policies, and how to write SQL code to extract these features. Because, as I've already said, the data is never written in the format that is suitable for our analytics. You always need to do some transformation. And that refers to the other part. So how do we build now, once we, let's say, identify the right data set, how do we build the code that will transform it? How do we put it into pipeline? And this is where the data efficiency matters. It thinks over, we have data engineers that are in charge to run data pipelines. So we have data engineering team basically that puts all the pipelines into production. But for data scientists, it's really important for every new feature that they build that it is efficient, because it's really impossible to actually have a data engineer assigned to every data scientist to work on feature engineering. So it's really important to actually transform this data to build the features in such a way that it can be used in production, because the code efficiency will matter. For example, when we are building the data transformation during building our model, we really need to think about the moment that if that goes to production, we will have 0.5 seconds or less than that, in most cases less than that, to prepare this information in this vector, serve it to the algorithm, get the prediction value, and then serve to the other application that will use this information for decision making. Of course, in many cases, we work with disparate data sources, with SQL, non-SQL tables, text files, log files. So there's different stuff there that we really need to know how to tackle and how to read from them. Also, data science, of course, is a teamwork. Actually, everything today is a teamwork. But what is really important when we are working in the team, where we have different persons that build some features, that train models, that deploy models to production, that then try to deploy a new model, that build all these pipelines, is for our code, in the first place, to be explainable. So the holy grail of every engineering project to write a proper documentation. It's not happening in most cases, but that's the holy grail. That's where we want to go through. Of course, for all of our code to be reusable. If we are working on some project for one department and in the next few months we will be working for other department, why not being able to reuse the same code? So we really need to think about how to structure this code properly so we can actually use it for different projects and also to be used from different people. And of course, not to create silos. So what here really matters is this body GitHub. This is really a gift that you can see on many presentations. But actually, that's the point of GitHub. So all the work that we do on any project really needs to be shared somewhere. So we really need to version our code, because it doesn't matter if I'm working in a team. For example, if I was working on some problem 2 years ago, and now I need to change something, or I don't know, 2 months ago, well, after 2 months I will probably forget what I tried to achieve there. So it's much easier if I had different versions of code to see what I changed through. And also in this way, all of our code can be shared within a team, so we can actually work as a team on one project and not just have silos like you go do this and you go do that and that's it. And yeah, you can see here what I added to Git ignore. So for people who know how to use GitHub, I'll get to that later. Why I ignored all the Jupyter stuff from the Git repository. This is one of the flows. It's really popular for software engineering that we use at ThinkSolver, how to code version our applications. It's called Git flow. And the basic idea is like you have for every, let's say for one application, you have a master branch on GitHub that says, okay, this is the production code. So everything on this branch will be working. It must work like 100% of the times. So that's like something that's the master version of our application. Then we have a development branch where we do all of our improvements. So everything that we build new, we push to development branch. And below we have feature branches. So let's say we are working for some marketing use case. So we can put one feature, let's say the recommendation system, and put all of our code into this branch. Then segmentation is another branch. And once we are finished with one of these tasks, they are all merged to develop branch, where we test everything. When we are sure that this can be running in production, we can then merge this add this to the master branch and actually have a new version of our machine learning application. So it's not only for machine learning, it's for any software project that we can work on. And you probably know what is this. I'm actually have a lot of negative things to say about the Jupyter notebooks and the way that people use Jupyter notebooks. But of course, Jupyter is really helpful for us when we do some exploration, when we try to do some proof of concept to see whether some approaches work. Actually, as a data engineer, I also use Jupyter notebooks to connect to the database, to just read a few data, to try some transformation. But writing code in Jupyter notebook, it's not a product. It's okay if you're doing some research, but if you want to build a solution that really can be implemented for your clients, for your customers, then Jupyter Notebook, it's not a product. Why is that so? First of all, code versioning doesn't work. Basically, if you just open Jupyter Notebook and save it, GitHub will see that you made some changes. You cannot see which changes, because actually you didn't write the code there, and that's the way it works. Also, code styling, code testing, it's really hard to implement. And one of the things is, of course, state dependency. So as you can see here, what I can do with Jupyter Notebook, I assigned the a equals 1 in this cell, and then I wrote print a below. So since I am the one who controls how this code will be executed, I will first execute this cell and then that cell, so the code will run. If I try to do anything with that, it will fail because that's not the structure, that's not how the Python program is executed. This is just an interpreter for us to work interactively with the data. Of course, ID integration. At the end, since we have many people in the team, we of course need to find proper ID because we need to put all of the pipelines there, ETLs, the ways that we will serve the data in one place, and Jupyter is definitely not a tool for that. So what is the difference between these two stuff? Building a model in Jupyter Notebook is just one of the portions of the application that we try to build. It's completely different from building a robust model that will run in production. And why is that so? Well, there are different KPIs that we need to achieve in order to use the solution in production. First of all, pipeline in automation. We have built our model. We need to put this into ETL, into some sort of pipeline, so our data will flow through all the steps that we need to add, like different transformations, transposes, and whatever we do with our matrices. Quality assurance, how to make sure that everything that we worked on will be running after implementing some changes, because our data changes. One of my friends actually told me that I'm in a good industry because data science is like self-sustaining job. So you build a model, you put it into production, then you change your business processes, then your data changes, so you need to build a new model, so it's a repetitive task. You just go to improving your business, and basically we are safe with our jobs. Of course, builds and deployments, how to deploy everything into practice, how to monitor the flow, how to integrate with different tools, and of course, how to scale. So I'm not saying that data scientists should know all of this, but I believe those are the crucial areas that data scientists should be aware of. If you are talking about the scale, so now we have a data set, let's say we are a new customer, we are a new company on the market, we only have dozens of customers, so we are running a recommendation engine. We, data scientists and actually the whole team needs to think about, will this code work if we have 100 customers, 1,000 customers, and how to be able to scale it when we achieve these levels of business. How to automate our pipeline. Of course, it's always about the code efficiency, so really to make sure that our code is efficient. What I usually see from the new data scientists that come from academia, if they are working with the databases, they tend to use pandas to load all the data from database and then do the transformation in pandas. And that's like 100% slower than writing some queries in SQL and use your database engine to process this data, because database engines are built for this, to implement these transformations. And they will definitely, in 99.9 cases, they will be faster than running all of this in pandas or some other library. At least you don't have to transfer data from your database to your local machine where you're doing the processing. That's another portion. We also need to think about where our data is located, so how to properly use the network throughput, whether we have enough of the network to get all this data into our notebooks, our coding environment, so we can implement all of this. So here are some of the concepts that are quite relevant here. So if you're talking about the scale, how to write distributed code. If you're talking about integration, how to properly design those APIs that you want to serve. How to implement logging, because not all these tasks are primary for data scientists, but if you're talking about the monitoring of certain machine learning model, of course that's something that data scientists will build better, because as data engineers we have no clue how to monitor a data model, what is actually a good measure of performance of a model, whether it works or not. And here are some tools how we actually do it. So what does one of our solutions, what does it look like in practice? So we have, first of all, CI/CD pipelines. So everything that we write, we aim to be completely automated. So if anything is changed in code, we want to, on our master branch, we want to deploy it to production. How this works, how to make sure that we didn't break anything. Of course, we need to write tests for different steps in our process. What next? How to make sure that nobody made any changes is actually to add code review process. Those are all the changes. When we started the company, we didn't work that way. That's something that naturally happened for us. We just figured out that we need to add code review, because if I'm working on some stuff, I will have some perspective, and there are probably many areas where I can basically forget about the problems that might occur. So that's a really good idea why you should have a code review process, because more people will look into your code, first of all, try to understand it, basically give you feedback whether something you write is really understandable, or if you just you're the only person that knows what's running there, and to actually remove the potential bottlenecks. At the end, we aim for all of our solutions to run independent of the infrastructure, so we basically put all of our machine learning pipelines in Docker containers. Actually, Docker here and Kubernetes, on the hype that is there on the market, it's for a reason, because we are now able to have a microservices architecture, so everything that we build is naturally added as a new application on top of the product that we are building. This one, of course, pipeline efficiency. So this is something where, of course, the management will care whether your code is efficient, or you just forgot to add some stuff to the code, and then the invoice from your cloud operator can really be huge. Sorry, I just have to go back to this slide. Why is code versioning important? Because one of the clients that we are working with, they're a company from US, really huge company. They don't have the code review process set in place for one department, and since they have open source project, they left their credentials to GitHub repository. There are, of course, different people that just scrape different repositories that search for your API keys. So they got a 10K invoice because somebody just found on GitHub their token for AWS and just launched some machines. And of course, at the end, it always comes to, does the model worth the investment? So it doesn't matter that we build a super cool model that has, deep learning, different neural networks implemented, that runs a GPU. If it cannot basically cover the costs of the improvement that we bring to the business, that's something that's really crucial to be sure how to implement the code that will be efficient and that won't actually be spending more money than we earn. So what is actually data science? It's definitely more than pure analytics. So we have interconnected processes, iterative, adaptive, and that should be automated. And of course, at the end, it all comes to the learning. Nobody is expecting actually from data scientists to be a top coder to know everything about the Kubernetes, how to run a Kubernetes in production, how to serve, 2 million users. But it's definitely the area where we should definitely focus, and it's really only by learning and by doing, it's how you actually learn all of this stuff that is relevant to build a data product. Yeah, that's it. Thank you.
We have just one question or comment. It's about your slide with the iceberg. Mm-hmm. Don't you want to return to it, okay? Yep. Oh, yeah, okay. Don't you think it's actually the opposite? Academia teaches us depth, and in practice we use APIs and libraries.
Okay, can you repeat?
Academia teaches us depth, and in practice we use APIs and libraries.
I'm not sure, actually. It wasn't my experience, because I believe in most cases the focus is on modeling, on how to build models, how to evaluate the model, and not actually on how to use APIs and different... I'm not sure if I answered your question. Hopefully.
Well, we'll see. We'll see. So, whoever asked you the question can find you later so you can have a chat about this. Yeah. Milos, thank you.
Thank you.
Here's your certificate.
Thank you.